All right, I think we're recording. I'm going to pull in together the last topics for our semester. So looking ahead, we've got two more, well, today and then Monday's class. We'll finish this off for material. The review will be a week from today. So I cover all the stuff. Final exam should be Wednesday of finals week. It will be according to the schedule. I'll make sure there's an announcement out there sometime next week for the exact time. One of the things to remember on finals week, most classes do not meet at their normal time. It'll either be on a Monday or Wednesday if your class is on Monday or Wednesday. So it'll meet on the same day of the week as your class normally meets, but the blocks of time are cut up into 2-hour segments. And so you're almost guaranteed that the class start time will not be the same on finals week. So I'll make sure that's posted and you have the announcement. It's also, if you go to the UCCS website, you can look for finals week schedule and then read it carefully. I've occasionally had students panic because they thought they had two finals scheduled at the same time for two different classes. So that's technically not possible with the way they do it. It's made, if the classes don't meet at the same time, then the finals won't overlap either. But occasionally teachers, I am told, try to change the final exam time, which is a really unfortunate thing to do. So we will not do that. So you can plan on whatever the schedule says. That'll be our final exam time. I plan the final exam to be about an hour and 20 minutes, not using the full 2-hour. So it'll be about the same size as our normal hour and a half. And it'll be about 20% cumulative. So cumulative means it will be the big ideas off the other two exams. I would not have you do extremely detailed analysis, but on the review sheet, which will be out, I should get that. I'll get that out so you have it for the weekend, for this weekend, and we'll talk about it a week from today. But the review sheet will have the cumulative stuff that you should aim for. We'll do you can bring a sheet of paper. Still, at the moment, planning one-sided, but we'll see if there's actually a crazy amount of stuff that you need 2 whole sides of this paper. Okay. There may be one more homework set of questions that I'll get posted. Let's see, it'd have to be due in a week. It'd be small if there is one. Okay, so we want to hit one more topic out of undecidability and then finish up our discussion of the classes of problems. So an undecidable problem is one that you can't solve, right? I mean, essentially, undecidable means Well, you tell me, what is undecidable mean in reference to a problem? An undecidable problem comes back thinking in terms of maybe Turing machines.
Doesn't accept or reject in finite amount.
Yeah, yeah. So we can't come up with a solution that is guaranteed to stop for every input. You want to avoid the mistake of just looking at a single example, say, and saying, well, no, wait a minute, that's not undecidable, because if I give it exactly this input, I can make it stop on this. That's not the statement of the problem, right? We'll look at, in a moment here, the post-correspondence problem, which is kind of a classic one of the problems that we see in the whole complexity theory, computability theory, and we'll describe that. You could come up with a particular instance of it that is solvable. But in general, it's an undecidable problem. So, and we're really talking about not an issue, and this is kind of a subtle point. Sometimes people miss word saying that the problem itself cannot be solved. It's not a matter of we just need to have a smarter approach to it, but it's provably undecidable. So anything it's undecidable is not guaranteed to So it's not guaranteed to stop with a yes or no answer in a finite amount of time. So over in chapter 5. Oh, I did want to. Repeat our just to refresh our definitions. This is still significant that, and we had a number of statements when we started into the section on decidability, things that all regular languages are decidable, and context-free languages are decidable. So, a good kind of reference way to represent that, to think about that, is to see that they are in the realm of, or they're subsets of all the decidable languages. And there should be a fairly logical, right, intuitive sense of that. Regular languages, you can plug it into a DFA. DFA is deterministic, has one move per input character. You just simulate it on a Turing machine. Context-free languages, similarly, we can run them into a PDA, and we can figure out whether a given input is valid or not based on, remember, our whole process of going through the stack, and if we can end up with an empty stack and an accept state with no more input left, then we can determine, we can decide whether a given string is part of the language. Turing, we got into, so the broader sense of solving problems, like addition, subtraction, math operations. We want to look at one more instance for Turing machines that we have not, that were part of the final, but we'll touch on that. But then Turing recognizable said we can tell if a string, if the ambiguity or the problem is, if a string truly is in the language, eventually it will stop and say yes. But if the string isn't in the language, we don't know. It may say no for Turing recognizable, these guys out here, or it may not ever stop. So yeah, so these guys are nice and will stop and are decidable. So the post correspondence program, no problem, or PCP. Goes like this, and there are a few different formulations of it as substrings, but I think the most tangible one for picturing it is the one actually from your book, which is the idea of little, think of it as dominoes that have one or more characters on them. So each one, there's an upper half, lower half, obviously. And this trivial example. Sure. Here's one. So just to illustrate the simplest sense, given a set of say tiles having an upper, having two strings on them. This is a yes or no problem. Does there exist ordering with upper and lower? Okay, so the question is, can I take, and this is misleadingly simple for the first example, but can I take an ordering of these tiles such that the reading of the top string will be identical to the reading on the bottom string? Okay, so just to lure you in with really simple example. So this says, given a set of tiles with 2 strings on them, does there exist an ordering potentially with duplicates, giving a matching upper and lower string as the results? Does that make sense? You gotta understand the setup. So first of all, looking at the simplest example, do you think there could possibly be a way that you could arrange those to have the upper string read identically to the lower string? Yeah. So the clear answer to this one is yeah. And so I did it on purpose to illustrate. But you can imagine if we start changing it up where they're not in order initially, and we can mix it up. Let's see, does that make it? Let's see, I wanted to get let's there we go. So is there a way we can arrange these so the upper and lower strings read the same way? Well, and let's just analyze a little bit. We got a BC here with an A on top. So to get the BC in the top, we don't have 2 together, so we would have to use this, right? So if we have, let's put that one at the front. Can we have to put the yeah, okay. So what we have to do is start. Oh, this looks bad already. Looks like a pretty immediate fail there. Well, we can do the same. Yeah, this is not clearing up the problem.
No.
No. The intention was to
Unless you can.
so that there's not. I think as soon as we have some, let's see. If we do that, then these don't solve the problem because you need to have something with an A out front. Yeah, it gets messy fast, right? And you can see that finding a solution is not immediately evident.
I mean, you can't just the bottom part or the top part to another one.
Let's see, let me, so if you're, let me put up the one from the book. I'm on page 227. Got it? Oops. Okay, so using this set, can we get a match? So with a little trial and error, we can get, there are some rules here that you have to be able to generate the prefix, right? So an ordering for that guy could look like
A. Where did the extra A come from?
they say, oh, you can have duplicates with duplicates. Oh, yeah, okay. And then the bottom is this guy. So this is an example of this guy's, obviously.
What do we want to do?
That's just the way the problem is. Allows duplicates. So we're just asking, can you arrange these? Can you find a sequence of these with duplicates potentially that will result in a configuration where the upper string matches the lower string? As soon as you throw in the with duplicates, becomes more obvious that you can't just try every combination immediately, because the thing is unbounded as far as soon as you say duplicates, you can throw in more tiles. So it's not like you just have 4 tiles that you can, right? If you just had that, can you solve it? Can you arrange 4 tiles in some way to check that the upper and lower strings are the same? Think you can do that?
No.
Maybe you
I don't understand.
could.
What's the answer.
Oh, what's that?
Is this an answer?
Well, my question is, if you're just given 4 tiles like this, is it possible to determine in a finite time and come up with a yes or no answer? Just, can these 4 be arranged without any duplicates to get the same upper and lower? Is that decidable?
Yes, yeah. Only a certain number of ways.
Right. It's just every permutation, right? So that's like a factorial problem, which is not pleasant, right? It is not it's not polynomial, right? So just an order of n, but it is doable, right? I mean, if you just had these, start with, put a little number on each one, if you want. I didn't say it was going to be efficient, but start with 1 at the front, 2, 3, 4, then shift 2 to the end and do 3, 4, 2, and then shift it, do 4, 2, 3, right, into every combination, every permutation of position with 1 at the front, and then put 2 at the front, and then do the same, go through the whole thing. It's factorial in the number of different ways you can arrange it. But it will stop. So the undecidable element comes in when you allow duplicates to be put in, and you've kind of taken the boundedness off from here and turned it into an undecidable problem. You're not guaranteed that you can stop and find an answer. This is comment. He gives an example of one where all of the upper substrings are longer than the ones underneath them. So it's sort of self-evident that you can never get a match every time you, right, if you had something with, how many does he use? And am I running out of room? No. Right, so this is kind of immediately obvious that you'll never be able to get the same number of characters, right? Every time you add one of these, you're adding 1 fewer letter to the thing. So there are some sets that you could look at and immediately do a check, right? Say if every lower string is fewer characters, or vice versa, every upper one has fewer characters than the lower one on that tile, then we can answer no. But it's back to that general problem of taking some set without any restrictions on it and having to come up with whether I can find a match with it or not. So it's not algorithmically solvable. So we want to contrast our undecidable problems with, let's see, basically theorem 515 in chapter 5 is that PCP is undecidable, and goes into some detail on the proof of that. Which we're not going to spend time on. So this is in the, we've kind of crossed, I guess, our line between decidable and recognizable. Kind of, I want to, it's easy to get mixed up because we usually introduce decidable versus undecidable with in close proximity to the whole P versus NP problem, considering two different classes of computational complexity. So we saw that so solving the PCP for n dominoes with no duplicates, is that decidable? Yeah, right. It's the permutation problem. So is it P or NP in its complexity? It'd be NP, because it's I give it away with the factorial, right? 2 to the n to the n factorial are all examples, not certainly exhaustive, but common examples of the kind of time complexities you run into. But as soon as we say, is there any way to do it, and you can have duplicates, then it becomes unbounded, and it goes into the realm of you can't actually solve it. So try to get some takeaway points. Oops. So kind of the problem is that we're concerned with the complexity, the time complexity, are decidable, right? I mean, as soon as you get to undecidable, then it really doesn't matter because they're going to run forever and ever, potentially. The undecidable nature is it might stop, it might go on forever. We just have no way of telling. But when we start talking about the complexity time-wise, we're talking about decidable problems. An open question. I guess what this means. We're talking about two different classes of problems, and we kind of drew to try and give it some kind of an image. Oops, that's supposed to be a straight line. Kind of went down the path of. Right, so here's kind of the poly. Right, we're graphing what n versus time. And we said anything that's n to some constant d, those all fall under the p side of the graph world. And I think we emphasized because you can put coefficients on these, it may not be real evident when you have fallen off the edge of the world and gotten into the. And you thought there wasn't an edge of the world. Right, so we can label even though you might say some of these might take a really long time. You could have a high power of n, right? D is 50. It's like n to the 50th power. That's going to take you a while to run. But the speed with which those functions increase is small compared to non-polynomial, which is not that mean, non-deterministic polynomial time. The algorithm just points out that the worst thing you can ever say is that that means non-polynomial or not polynomial. All of these are in that realm of the intractable. Things you can't solve them for other than very small values of n. I think I mentioned kind of hitting, sorry if I'm hitting same thing. It's always good for students to see the same thing a couple of times. The algorithms class, we're approaching it a little bit differently on the discussing the P and NP classes of problems, but I think we talked at somewhere. I mentioned the towers of Hanoi, which is a factorial times problem of moving disks around, and for n equals 64, it takes like at something like 1,000 operations per second. It takes a couple of trillion years to solve. So for a tiny n like 64, when you're applying it in a factorial problem, it's unreasonable to solve it for all but the smallest values of n. And I did want to emphasize that there is all of our discussion is said not so much the mathematical theoretical goes to infinity like a limit, right? But rather as n gets large, and we're implying that that the big N that we're concerned with is not um, in the trillions or quadrillions or super huge, but big relative to the fact that, oh, this is still within the realm of something I would want to do, right? That this is a reasonable amount of input. It's not it's not in the theoretical world where we don't care about, the N is so huge that we never even bother trying to solve a problem with that. We're talking about N's of 100, 1,000, a few thousand, where like for the towers of Hanoi, even a value like 64, which seems relatively small. The problem is unsolvable in the time that the world has existed. So to point out, if the question, so we have identified, and there people have been working on it for decades, classes of problems that are definitely, we only know solutions that fall up here, and they are way worse than the worst of problems that we find over here in the tractable side. So the speculation, this is still an open issue for reference. Because we haven't been able to mathematically prove that they are not equal. The speculation that I guess the most likely outcome is that the two classes are actually separate. The alternative is that somehow we just haven't been smart enough. We haven't figured out how to get those NP problems into the right form, or find the clever enough algorithm that really there is a polynomial solution for them. We just haven't discovered it yet. And until there's a definitive proof that that's not the case, that there's something inherent in those problems that you can't possibly solve them, which again, on the surface, that's what it looks like, but there's not a definitive proof. So it's reasonable to live your life as if this is the case and to solve your problems with that in mind. So the practical side of all of that, in the other class, somebody came up after class and was mentioning something at work that had a problem that had come up, the manager had brought up, and then all the earmarks of it was similar to another NP problem that we had discussed in class, and he's able to identify that, basically the question, the typical manager question is, well, can you write the code to do this for us? And he was able to do some analysis on it and recognize, there are not going to be really fast solutions for this in its raw state, in the way the problem presents itself. And so what you typically have to do in the real world is come up with compromises to get a good enough solution. So when we talk about the problems that are intractable, the solution is usually find some way to limit the accuracy, right? In other words, accept a less accurate answer, or accept a partial answer, or come up with something that's good enough. I think we used the example of the traveling salesman problem, where you may not have to find the actual ultimate optimal solution, the very shortest, right? The traveling salesman goes to every city every city in a circuit, visiting each city once at the minimal cost. There are algorithms that would, and it's kind of what you would naturally, right, intuitively pick. How would you solve that if you're, check how intuitive you are. If you had may or may not be totally connected, I guess. And try some, for example, how might you approach something like that? The ultimate answer would be to try every possible combination of edges, which gets you into the ugly factorial or worse realm. But could you come up with a solution? What would you do? What would you do if you didn't even care about the weights? How would you make sure that you hit all the vertices?
Go down every edge.
Start at one of the vertices and just take each edge, right? So you could start by sort of a refinement process. One approximation way to do it would be, okay, let's just try to find a path to every single vertex. And there actually is a way to do that in a reasonable length of time. And then add up what the scores are, add up what your weights are on the first pass, and then try to progressively refine that by saying, okay, can I substitute between here and here, what are the possible, right, I could find a path, and this is one of those where you could reasonably, right, to get from here, if getting from here to here is your goal, then options would be the direct, or here to here to here, or here to here, take the long route around. And so you could kind of tabulate those, and once you got an obvious sort of circuit around the thing, might be just that. Or, right, you could kind of go the other way around, and this looks kind of bad. If you could avoid that 12, that would be, oh, I guess you can't, because you have to go through, we need more edges.
Yeah, probably.
We have more edges, then we can have more choices, right? But anyway, the point being, coming up with just a solution, right? If you can just get, it may be that in the real world, you would pick a series of cities and just go to all of them, and it might be sometime later that you discover there is actually another route that you could take that would maybe shave off some miles or something. So the perfect solution is going to be very time consuming, but maybe a good enough solution is I don't care the difference between 100 miles and 115 miles, right? I mean, we do that kind of thing all the time if you're taking a road trip and trying to figure out we want to hit these different spots. Usually we're not real concerned about actually passing the same place twice necessarily. Okay, and this is about where we're going to get with the P versus NP kinds of problems. The things I highlighted here are the kinds of things I'll make sure we'll get I'll get a review sheet out probably by tomorrow. This point in the game, but so you have it over the weekend, and then we'll be able to clear up any loose ends on Monday. However, I will also give you to work on an example of I'll put it in just take a couple minutes here to describe it once. I'll put it in words, and then I will have something about Turing machine solving an actual problem. So I'll state the problem and so given a Turing machine an input that looks like okay. What's that? No, this is I don't know that we did a Turing machine solution. Oh, you did one on the last homework. But this is just a little more extensive, just to make sure you got it. So we didn't cover this on exam number 2. To determine, write pseudocode to determine if the count of ones on either side of the dollar sign is the same. Okay, so just to, there will be, so I guess this is prep. We talked through these, we did a couple of examples on the Turing machine of it moving back and forth, but just to solidify that, essentially I'm going to give you this problem written to write up a little pseudocode description of what it would have to do. Move to the left until it sees this, cross off this one, move until you see the dollar sign, move until you see the other pound, whatever. Just to count and see. The whole point is you don't care about, it can be destructive of the input. And all you want to do is end up with a Y or an N. Y if the number of ones is equal to the number of ones on the other side of the dollar sign. And to put an N if they are not equal. All right, so just to work through one of those kind of problems, give it a thought and nail down the Turing machine stuff. What's that? All right, so that will do it. I will. I'll send out an announcement before the weekend if there's anything else I left out for you to read here. This book, I like the first part of it a lot. With the he does real well on the descriptions and seems to be
And now it's going all over the place.
good to work with. And then
And then it just goes into algorithm.
yeah, then it kind of gets. He's definitely heavily focusing on the mathematical proof side and stuff that I think goes outside our realm of practicality. All right, so we'll reconvene on Monday. I'll give you a heads up on the content for Monday to read ahead, and then Wednesday, a week from now, will be strictly review and exam. I think we decided, is somebody look it up in here for, I believe, Wednesday?
Yeah, Wednesday.
Yeah.
I think it's 1, 2, 12, 20, 2, 20.
I'll make sure that's announced as well, so nobody gets left out. But yes, try to not have you left behind.